All right, let's turn this down just a little bit. So greetings, YouTube. Let's turn it down just a little bit more. All right. Beautiful mind here, and we're just going to continue with the next lecture. This is for Calculus for Business. This is the second part of day 2. We're gonna be doing section 1.2, algebraic limits and continuity. So some objectives here are to develop and use the limit principles to calculate limits and determine whether a function is continuous at a point. So some limit properties. If the limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x equals m, and c is any constant, then we have the following. The limit of a constant is the constant of a limit. So as x approaches a of a constant, if it's a constant, that means it's always going to be the output. So it should be that same number, right? So the limit of a constant is the constant. The limit of a power is the limit of the base raised to that power. So the limit as x approaches a of the power of a function is going to be the power of the limit. So long story short, the limit of the power is going to be the power of the limit, if that makes sense. The limit of the root is going to be the root of the limit, assuming that the limit is non-negative. When n is even, when the index is even, because we can't take the even root of a negative number. So whenever we're dealing with roots, we do have to be on the lookout for that. Making sure that if the index is even, making sure that the radicand is non-negative. The limit of the sum or difference is the sum or difference of the limit, right? So here we have the limit of this sum or difference is going to be the same as the first limit plus or minus the second limit. Right? The limit of the product is the product of the limit. So the limit of the product is the product of the limits. The limit of the quotient is the quotient of the limits. Again, provided the limit in the denominator is not 0. The limit of a constant times a function is the constant times the limit. So a constant times a function is going to be the constant times the limit. Okay? So these are just limit properties. So then we're actually use the limit properties to find this limit, right? So we have the limit as x approaches 4 of this. I want to say essentially here we can just plug in, right? So 4 squared is what, 16? Let me see. Let's see if this works. So that's going to be what? 16 minus 12 plus 7. I just plugged it in. 4, that's going to be 11, all right? Let's see if 11 works. You see it there. Okay, I mean, and you can justify those steps with the limit properties that we just saw. Hopefully my mic isn't turned up too much. I switched my mics because I realized that the last couple of presentations the audio was really low, so I got a better mic, and now it seems like it's too loud. That's life. Anyway, moving along. Let me clear this off and put this back. Okay. So limits of rational functions. For any rational function f with a in the domain of f, the limit as x approaches a of the rational function is going to be f of a. So find the limit as x approaches 0. Should just be the square root of 2, right? Because like the limit of the root is going to be the root of the limit. The limit of the sum or difference is going to be the sum or difference of the limits. Long story short, it's kind of like we're just plugging in. It doesn't always work, but that's a good place to start. All right, so then we just get the square root of 2. Okay, as x approaches 1. It looks like the first one, if we just do the same thing that we've been doing, looks like that's going to be what? 2, 5, negative 1? It looks like that one is negative 1, right? Let me see, 16 times 2. What is that? 32 plus 20 minus 1. 12 minus 2. What is that? 50, 52, 51. So 5.1. We'll check it in a moment. 4 times 3 is 12. So that looks like it's going to be the square root of 13. Let's see if these worked. Here's a negative 1. I'm going to get rid of these. Well, we can confirm the -1, 5.1, and square root of 13. I'm going to clear these out just to have clean notes. Okay. Let's see. Now notice here, if we try to just plug in -3, I think we get 0 over 0, right? So we can't just plug in here. But we can simplify this, and it should give us a sense of the limit. So x squared minus 9 is the same as x minus 3 times x plus 3. Those x plus 3's cancel, so then you have -3 minus 3 gives us -6. So even though this limit is not defined at this function is not defined at -3, it looks like the left-hand limit equals the right-hand limit. It should be -6 in this case. So as x goes off to infinity, I kind of wish I had prepped this one, but we'll use the slides, right? So as x goes off to infinity, now we can't just plug in infinity directly because I think we'll get infinity over infinity. So what we can do is factor out or divide the numerator and the denominator by the highest power in the denominator. So if we divide each term by x squared, we get the following. So the first one turns into a 1, then we get this result here that you see. All right. So now if we let the limit as x gets really large, the first one stays as is. 4 divided by a really large number, this is essentially 0. This is essentially 0. This is 0, and this is 0. And so then we're left with 1 by 2. Okay. I think it's similar here, right? If you try to just let x go to infinity, you'll get infinity over infinity. So we can use a technique of dividing each term by the largest power in the denominator. So we're going to divide everything by x cubed. Factor out x cubed from the top and the bottom. We'll get this expression when we do that. And then as we let x go to infinity, this goes to 0, this goes to 0, this goes to 0, this goes to 0, and this goes to 0. So then we're left with 2 by 3. Let's see my time. This one's actually fairly short as well. A function is continuous at a if it's defined at that point. So the output at a exists. The limit as x approaches a exists. That means the limit as x approaches a exists. And then if the limit as x approaches a is the same as f of a, then we say that it's continuous over an interval. Okay. So is this function given by this continuous at 3, right? So first we evaluate f of 3. If we plug in when x is 3, we get 9 minus 5, we get 4, right? The limit as x approaches 3, you can use the limit properties of rational functions. It's essentially the same thing. You can also do like the chart, like where if we looked at as x approaches 3 from the left, as x approaches 3 from the right. In either case, they're all going to approach 4. So since the left-hand limit equals the right-hand limit equals the value at the point, then we say that the function is continuous at 3. Okay. So hopefully during class we'll be able, not hopefully, but we'll be able to work some of these together during class. I'm just making this for you to kind of watch at your own rate, and we'll go from there. Is this function continuous at -2? All right. So if we plug in, like when x is -2, we're going to use this line, so the output would be -3. So g of -2 is -3, but then coming from the left is going to be this one. Looks like it's going to be -2. Let's see, just 2, right? Yeah. So as x approaches -2 coming from the left, we're going to use the first line. I mean, I really did just plug in -2, but you know, if you're not convinced with that, you can do coming from the left of -2. You can make a table and look at like -3, -2.5, -2.1, -2.01, and you'll see that coming from the left, it'll approach -3. sorry, coming from the left, it'll approach 2. Coming from the right, it should approach -3. So the limit as x approaches -2 from the right approaches -3. So notice that the limit from the left is not equal to the limit from the right. And so we say that this limit does not exist. So therefore, g is not continuous at x equals -2. Okay, let's see. Let's just look at this really quick. So is this continuous at 2, why or why not? So let's see, coming from the left of 2, we're going to get 1. Coming from the right of 2 is 5. So we would say no, right? So notice that g of 2 is 5. Coming from the left, we get 1. Coming from the right, we get 5. So then the left-hand limit is not equal to the right-hand limit. So therefore, the limit as x approaches 2 does not exist. So therefore, because the limit does not exist, g is not continuous at x equals 2. Is this continuous at 3? Okay. So coming from the left of 3, I think we just did this one, right? Let me see. We can't just plug in 3 because this first part is not defined when x is 3. But we can simplify. We're going to be left with x plus 3, so we get 6. Right? Because you can't plug it in here, it becomes undefined. So if you simplify, these cancel. Then now we can evaluate the simplified version and we get 6. But when the function says that when x is 3, it's a 7. So the limit as x approaches 3 is going to be 6. But when x is actually 3, the value is 7. So because the left-hand limit does not, because the limit does not equal the value at the point, then we say it's not continuous. Right? So it's not continuous at x equals 3. Okay. Determine C such that P is continuous at x equals 5. Oh, find out a C. Okay. So then we could just find the limit as x approaches 5, and then whatever that limit is, let that be the C. If we just plug in 5, I think we get 0 over 0, so we would have to simplify. We'll get this. We can cancel those out, so then 10, right? 5 plus 5 is 10. So then let C be 10. So in order for it to be continuous, just let C be 10. And we'll get the desired result, or desired effect. Okay. Let's just kind of touch on this summary really quick. So for a rational function for which a is in the domain, the limit as x approaches a can be found by the direct evaluation of the function at a. If direct evaluations lead to an indeterminate form of 0 over 0, then the limit may still exist. Algebraic simplification and or a table and graph are used to find the limit. So we could either simplify algebraically or use a table and graph. And formally, a function is continuous if the graph can be sketched without lifting the pencil off the paper. Formally, a function is continuous at a if the function value f of a exists, the limit as x approaches a exists, the function value and the limit are equal. This can be summarized: the limit as x approaches a of the function is f of a. That's what we mean by continuity. If any part of the continuity definition fails, then the function is discontinuous at that point. Okay. So hopefully I wasn't talking too fast. If you have questions, the beautiful thing about these pre-recorded videos, you can pause them, rewind them. You can actually change the speed. But as you have questions, you have to just write them down and ask me during class. I will be in contact with instructions on how to access me live and get your questions answered. And I'll show you how to access the homework. And more than likely, I'll be working on the homework during class. And I mean, everybody still needs to submit their own work. You're going to be submitted via Blackboard. And but if you need demos or if you want to see me work specific questions or anything like that, you can ask me during class. Okay. So on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.